Right, question 1. We've got the mean science mark for one group of 8 students is 65, and the mean mark for a second group of 12 students is 72, and we're asked to calculate the mean mark for the combined group of 20 students. So the first group has got 8 students and a mean of 65, so the total marks scored by that group is 8 times 65. The second group has 12 students and a mean mark of 72. So 12 times 72 will give me the total marks scored by that group. So altogether, the 20 students combined have scored 1,384 marks. So to find the mean for the whole group, I'm going to do the total for the whole group divided by 20, the number of students, to give me a mean of 69.2 marks. Question 2. Right, I've got some data here showing the prices of 6 shares on a particular day. And the data is 807, 967, 727, 167, 207, and 767. Now I'm asked to code the data using this formula. Y has got to be x minus 7 divided by 80. So here's my x, so I'm going to put y here in a different colour, and each of my y values I'm going to calculate by doing the x value, take away 7, divided by 80. So that gives me 10 there, 12 there, 9, 2, 2.5, and 9.5. So they're in red are my values of y, the coded data. I'm going to stay in a red pen because in part B I'm asked to use the coded data because I'm asked to calculate the mean of the coded data. Right, part B. So really I'm just finding the mean of these numbers here. There are 6 numbers in all and they add up to 45. So y bar, the mean of y, is 45 divided by 6. So the mean of y is 7.5. Right, use your answer to part B to calculate the mean of the original data. Well, if y equals x minus 7 over 80, then I can rearrange that to make x the subject, 80y plus 7. So x bar, the mean of x, is 80 times the mean of y plus 7. So x bar will be 80 times 7.5 plus 7. Thus, the mean of x will be 607. And that is question 2 done. Question 3. The coded mean of the employee's annual earnings for a store is 18. The coding used was that, so y bar equals 18, and I'm asked to work out x bar. Well, if I rearrange this formula here to make x the subject, then I'm going to get x bar. It's going to be 1,000 times y bar plus 720. So that's going to be 1,000 times 18 plus 720. Well, that looks like 18,720 pounds to me. Question 4. Different teachers using different methods taught 2 groups of students. Both groups of students sat the same examination at the end of the course. The students' marks are shown in the grouped frequency table. Okay, that's Group A. That's Group B. Work out an estimate for the mean mark for Group A and an estimate for the mean mark for Group B. Right. Well, I've got group data here, so I'm going to need to use the midpoint for each of these classes here. So for instance, that's going to be 24.5, isn't it? Right, so let's do the mean for Group A first. So one of them scored 24.5. We're assuming it's 24.5. 3 of them scored 34.5. 6 of them scored 44.5. 6 of them scored 54.5. 11 of them scored 64.5. 10 of them scored 74.5, so that's just 745 marks. And 8 of them scored 84.5. So that will be the total of all the marks scored by Group A. So if I want to know the mean, I will need to divide that total by the number of students in Group A. How many students in Group A? Well, I'd need to add up these frequencies here, wouldn't I? And they add up to 45. So the mean is the total number of marks divided by 45. So when I work that out on my calculator, I get 2,852.5 marks in total. Divide that by 45, and my mean mark for Group A is 63.39 marks. Now, what about Group B? Right. Well, in Group B, again, one of the students scored 24.5. Two of the students scored 34.5. 4 of the students scored 44.5. 13 of the students scored 54.5. 15 of them scored 64.5. 6 of them scored 74.5. And 3 of them scored 84.5. Okay, so that's the total number of marks scored by all of the students in Group B. So I'm going to need to divide that by the number of students in Group B. So if I add up these frequencies here, then I work out that there are 44 students in Group B. So I'm going to divide that total by 44. Now on my calculator, that total is 2,648. So I need to divide that by 44, and I get that my approximation for the mean mark for Group B is 60.18. Right, Part B. Write down whether or not the answer to A suggests that one method of teaching is better than the other. Give a reason for your answer. Well, I would say that it looks like method B is the worst one because you've got a lower mean. So my answer is going to be method A is better, and I need to explain my answer because the mean for Group A is higher than the mean for Group B. That is number 4 complete. Question 5. Write the lifetime of 80 batteries to the nearest hour. So this time I know that n equals 80. Are shown below in the table. Okay, so I've got group data there. Write down the modal class for the lifetime of the batteries, the most common class, the most frequent lifetime. Well, that's going to be this class here, because there are 45 in that group, as opposed to less than 45 in every other. So for part A, the modal class is 21 to 25 hours. Right. Okay, part B. Use interpolation, I can never say the word interpolation, to find the median lifetime of the batteries. Right, the median lifetime. Well, there are 80 batteries, so I'm going to look for the 40th. We need the 40th data value here. So 80 divided by 2 is 40, so we're looking for the 40th. Now, which class is that going to be in? Well, we've got the first 12, and then the first 30 takes me up to here, doesn't it? Okay, so it's going to be in this group here. Now, be very careful. What is the starting lifetime of that group? It is not 21, it's 20.5, because each of these times is to the nearest hour. So 20.5 hours. Now I'm going to need to make my way into this group here. how far will I need to go? Well, I've already got 30 batteries taken care of in the first 3 classes, so I'm going to need 10 more batteries. So I'm going to need to go 10/45ths of the way through that class. And how wide is that class? Well, it goes from 20.5 all the way to 25.5, so it has a width of 5. So that expression will give me the median lifetime of the batteries. That'll give me the lifetime of the 40th battery, and that gives me an answer of 21.6 hours. Right, part C. The midpoint of each class is represented by x and the corresponding frequency. Okay, so I know the sum of the lifetime, sum of the hours, as long as we're using the midpoint. Calculate an estimate for the mean of the lifetime. Right, well, that's okay. So the mean would be the sum of all the midpoints multiplied by the frequency divided by the number of batteries. So that's simply going to be 1645 divided by 80, which gives me a mean of 20.6 hours. Right, part D. Another batch of 12 batteries is found to have a mean lifetime of 22.3. Estimate the mean lifetime for all 92 batteries. Right, so I've got my 80 batteries here, and I know that their total is 1645. I've got 12 more batteries which have a mean of 22.3. So I know their total is 12 times 22.3, which gives me 267.6. So altogether, the 92 batteries have a total lifetime of 1912.6. So the mean for all of them will be the total divided by 92, the number of batteries, which gives me an answer of 20.8 hours. That is question 5 complete. Question 6. A frequency distribution is shown below. Right. Use interpolation to find an estimate for the interquartile range. Okay. So, how many pieces of data have I got here altogether? I have got 50 pieces of data altogether. So, given that this is continuous data, Q1 will be which data value? Well, 50 over 4, it'll be the 12th and a half data value. And in the same way, Q3 will be 3/4 of 50. It will be the 37th and a half data value. So I'm just going to find each of those data values now. So let's find the 12th and a half. Now, the 12th and a half will be somewhere in this class here, won't it? So that class starts at 20.5, and I'm going to need to go 7.5 data values into that, and it is 10 data values wide. And what is the width of that class there? It's from 20.5 to 40.5. It has a width of 20. So that will give me the value of Q1, which is 35.5. Right, what about Q3? Now, Q3, I'm looking for the 37.5 value. That's the first 30. So I'm going to need to go 7.5 into this class, 7.5 out of 12. So I'm going to have 60.5, the beginning of that class, plus 7.5 out of 12 times the width of the class is 20. So that gives me a Q3 of 73. So now I can find the interquartile range. It'll be Q3, subtract Q1. Gives me an interquartile range of 37.5. And that is question 6. Question 7. Right, I need to use interpolation to estimate the value of the 30th centile. Right, so I'm in after finding P30. Now, how many data values are there altogether here? 10, 20, 30, 10, 30, 60. There are 100 data values altogether. Right, so the 30th data value is going to be P30. Okay, so I'm after the 30th data value. Right. Well, the 30th data value is going to be the one right at the start of this class here. So that's going to be 20.5. All right, now the next data value I'm after for part B is the 70th data value. So where is that one going to be? So 10, 30, 60. It's going to be in this class here. Now that class starts at 30.5. Now how far into the class am I going to have to go? Well, I've taken care of 60 already, so I'm going to need to have 10 data values into that class, which is 24 data values wide, multiplied by the width of that class, which is 30.5 to 40.5. So it's 10. So that gives me a 70th percentile of 34.7. Part C, hence estimate the 30% to 70% interpercentile range. Right, so that's just going to be P70 minus P30, 34.7, subtract 20.5, gives me an interpercentile range of 14.2. And that is question 7 done. Question 8. The times it took a random sample of runners to complete a race are summarized in the table. Time taken. Okay. Right. Now it looks to me as if these are given to the nearest minute. All right. So use interpolation to estimate the interquartile range. Now I wonder how many runners there are here. Right. Add up those frequencies there, and I see there are 80 runners. So Q1 is going to be the 20th runner, and Q3 is going to be the 60th runner. So I need the time of the 20th runner and the time of the 60th runner. Okay. Right, time of the 20th runner. Well, the 20th, that's the first 5, the first 10. So the 20th runner is going to be in the 40 to 49 class, which of course starts at 39.5. Now, how far into the class is that runner going to be? Well, there are 36 runners in the class, and he's going to be 5, the fifth one of those. So 5 out of 36 times the class width, which is from 39.5 to 49.5. So the class width is 10. So that gives me a Q1 of 40.9. That's the time of the 20th runner. Right, what about the 60th runner? Where are they going to be? That's the first 15, right. 41, that's the first 71 runners. So they're going to be in that class as well. No, they're not. Come on, add up properly, please. Try again. 15 plus 36 is 41, 51. So I've got 51 runners to here. And so my 60th runner is going to be in this class here. So that class begins at 49.5. How many did I say there were up to there? 50. There are 51, so I need to go 9 runners into that class, so 9/20ths of its width, and its width is 10. So that gives me a Q3 of 54. So hence my interquartile range will be 54 minus 40.9, Q3 minus Q1 gives me an interquartile range of 13.1. Right, now I'm going to delete all that so then I can see the question to do part B. Right, part B. The midpoint of each class is represented by x and the corresponding frequency by f, giving, look at that, I've got the sum of fx, I've got the sum of the x's, and I've got the sum of the x squared. That'll be useful because I'm asked to find an estimate for the variance. Now the variance is the mean of the squares, so that's going to be sum of fx squared over, how many runners were there? 80, minus the square of the mean, which is the total of all the times, divided by 80 squared. So just take a quick look at that. That is the mean of the squares, and that is the square of the mean. So what have I got here? I've got 183,040, the sum of all the squares, divided by 80, minus the sum of all of the original data, not squared, divided by 80. That's the mean. Take away the mean squared. So that gives me a variance of, to the nearest whole number, 102. Okay, on your calculator, that should look something like mine, which was that. Okay, and then the standard deviation, of course, is the square root of that. Make sure you square root the whole number. Gives you a standard deviation of 10.1. And that is number 8 done. Question 9. The heights of 50 clover flowers. So n is 50, as summarised in the table. Okay, let's have a quick look at that. We're asked to find Q1. Now, this is continuous data, so Q1 is going to be which data value? Answer, the 12.5 data value. So where's that going to be? Let's have a look. Well, it's not in the first class, but it is in this class here. So the beginning of that class is 95. Now, how far into that class do I need to go? Well, I have to go 7.5 data values out of 10 through that class, and the class has a class width of 5. So that gives me a Q1 of 98.75. Right, now in the book here it says find Q2. Now I'm going to assume that's a misprint. I'm going to find Q3, because then that'll help me with part C. And I think if it wanted Q2, it would be saying find the median. So let's find Q3. Now, which data point is the third quartile going to be? The upper quartile, I beg your pardon. Well, it's going to be 3/4 of 50. So it's going to be the 37.5 data value. So where is that going to be? Well, it's not there because that's the first 15. But now I've got up to 41. So it's going to be in this class here. How far into that class? Well, 37.5 is the one I want. I've already taken care of 15 of them. So it's going to be 12.5 data values into that class. That's 12.5 out of 26. The class width is 5. And of course, the class begins at 100. So there we go. 100 plus a portion of the way to 105. And that gives me a value for the third quartile of 104.33. So hence, for part C, my interquartile range is going to be 104.33 minus 98.75, which is going to be 5.58. Brilliant. Right, part C. I'm asked to find the standard deviation. Right, I'm not going to need any of this, so I'm just going to delete it for now so that it's out of the way. Right, part D. I'm told the sum of fx, and I'm told the sum of fx squared. So the standard deviation is going to be the square root of the variance. And the variance is the mean of the squares. So that's going to be 516,112.5 divided by 50, because there are 50 plants, minus the square of the mean. And that's 5075 over 50 squared. So that's the variance in the square bracket. And of course, then that's the variance in the square bracket. And I would square root that to get the standard deviation. And so a bit of calculator action there gives me a standard deviation of 4.47. And that is question 9 done. Question 10. The daily mean temperatures are recorded in Cambourne during September 2015. Okay, there we go. So we go from 11 to 13, 13 to 15, and so on. Use your calculator to find estimates for the mean and the standard deviation of the temperatures. Right, well, I'm obviously going to be using the midpoints here. So I'm going to be using 12, 14, and 16. Now, to find my estimate for the mean, I've got 12 days when the temperature was 12. I've got 14 days when the temperature was 14, assuming these midpoints, of course, and 4 days when the temperature was 16. So that's the total of all the temperatures. And to get the mean, I'll have to divide that by the number of days. Well, the number of days in September is obviously 30 because my frequencies add up to 30. So I'm going to divide by 30, which gives me a mean, a T bar, of, let's have a look, 202 over 15, that's what I get on my calculator, which is 13.5 degrees to 1 decimal place. Good. That's part A half done because now I have to find an estimate of the standard deviation. So I know the mean is 13.5. Right, the standard deviation. First of all, for the standard deviation, I better find the average of the squares. So I'm not sure quite how one is supposed to write this, but I'm going to write t squared bar. There you are. This is the average of the squares, right? So I've got 12 days, and the temperature squared would be 12 squared. 14 days, and the temperature squared would be 14 squared. 4 days, and the temperature squared would be 16 squared. And to find the average of those, I'll divide by 30. Okay, so that gives me a total of, if I do that on my calculator, there we go. So I get 916 over 5 on my calculator there. So the standard deviation then will be the square root of the variance. What is the variance? Well, it is the mean of the squares, take away the square of the mean. There we go. Now, of course, don't use 13.5 here. Use the whole number. So probably best to write 202 over 15 squared. And that gives me an answer of 1.36 if I round that to 3 significant figures. Right, that's part A, estimates for the mean and the standard deviation of the temperatures. Right, part B. Let's get rid of this. Okay. Use linear interpolation to find an estimate for the 10% to 90% interpercentile range. So for part B, I'm going to need to find the value of the 10th percentile and also the value of the 90th percentile. Now, how many days are there altogether? 30. So the 10th percentile is going to be the third data value, and the 90th percentile is presumably going to be the 27th data value. All right, the third day. Well, that's a quarter. It's 3 out of 12, isn't it? So it's a quarter of the way through that. Starts at 11, and then I go a quarter of the way between 11 and 13. So it's 11 plus a quarter of 2 gives me 11 and a half for P10. 11 and a half degrees. Now the 27th one, where's that going to be? Let's have a look. Well, that's 26. So it's just at the beginning, isn't it, of that range there. It's going to be, what's that going to be? It's going to be just a quarter of the way into that. So that's going to be 15 degrees, the beginning of that, plus a quarter of 2, which gives me 15.5. So what will the interpercentile range be from 90 to 10, or from 10 to 90? It will be 15.5 minus 11.5. Okay, so simply 4 degrees. Right, let's look at part C. Let's get rid of that. Right, part C. Estimate the number of days in September where the daily mean temperature in Camborne is more than 1 standard deviation greater than the mean. Well, the mean was 13.5. And the standard deviation was 1.36. So if a day is going to be hotter than one standard deviation greater than the mean, it needs to be hotter than 14.86. So how many days do we reckon, looking at the table, had a temperature of greater than 14.86? Well, clearly those 4 days had a temperature greater than 14.86. That's 4 days already, plus a fraction of these 14 days. Now, what fraction of those 14 days? Well, if we assume those 14 days are evenly spread between 13 and 15, we want a certain fraction of those days. We want the days that lie between 14.86 and 15. So what fraction of the days will that be? Well, assuming those 14 days are evenly spread, it'll be 0.14 out of 2 of those 14 days. So that is my estimate for the number of days where the daily mean temperature is more than one standard deviation greater than the mean. And that comes to 4.98. Hence my estimate is 5 days. And that is part C done, and that's question 10 complete. Question 11. The daily mean wind speed, W knots, was recorded at Heathrow during May 2015. And then the data was coded to give us Z. That's the coding. Right, I'm told some stats around Z now. Well, N, of course, 31 is the number of days, number of Ws, and the number of Zs. I'm told the sum of Z, and I'm told the summary statistic of Z. Find the mean and the standard deviation of the coded data. So it wants the mean of Z, first of all. The mean of Z will be the total of the Zs divided by the number of Zs. 106 divided by 31 gives me 3.419, and so on my calculator. Now, what about the standard deviation of Z? Well, that's going to be the square root of the variance, and the variance will be the summary statistic of Z divided by N. So I'm going to do the square root of 80.55 divided by 31, which gives me 1.6119, and so on. So that is the mean and the standard deviation of the coded data. And now in part B, I'm asked to use those values, I guess, to work out the mean and the standard deviation of the original data of W. So W is going to equal twice Z, 2Z plus 3. It's not very legible, try again. 2Z plus 3, which is going to be, so the mean of W is twice the mean of Z plus 3, so twice 3.419 plus 3 gives me a mean for W of 9.84 kilometers. Now, what about the standard deviation? Well, the standard deviation will have been made, what am I dividing by here? I'm dividing by 2. So the standard deviation will have been made a factor of 2 times smaller. So the standard deviation of W will be twice the standard deviation of Z. So it'll be twice 1.6119, which gives me a standard deviation of 3.22 kilometers. And that's question 11 done. Question 12, last question. Here we go. Right, 20 endangered forest outlets were caught for ringing. Their wingspans X were measured to the nearest centimetre. The following summary stats were worked out. Okay, so from there, can we work out the mean and the standard deviation of the wingspan of the 20 birds? Well, the mean is going to be the total of the wingspans divided by 20. So 316 divided by 20, 15.8. Okay, now the standard deviation is going to be the square root of the variance. What's the variance? Well, it's the mean of the squares minus the square of the mean. So the the standard deviation is the square root of the variance. It's the square root of that gives me a standard deviation of 2.06. That is part A done. Part B. One more bird was caught. It had a wingspan of 13 centimetres. Without doing any further calculations, say how you think this extra wingspan will affect the mean wingspan. Well, before we caught that extra bird, the mean wingspan was 15.8. And our extra bird has got a wingspan of only 13. So that's going to lower the mean, isn't it? So we think the extra wingspan will lower the mean because the new one, 13, is less than the mean of the existing ones. Okay, right. Part C. Right. 20 giant ibises were also caught for ringing. Their wingspans were as follows. Right, before I go any further, I'm just going to delete all this so that I can see what I'm doing for part C. Right. So in part C, 20 giant ibises, N is 20, were caught for ringing. Their wingspans, Y centimetres, were also measured and the data was coded. Right. And then I'm giving some summary statistics about the coded data. Look, I'm given the total of Z and I'm given the summary statistic for Z. Let's just write down that Z is Y minus 5 over 10. Right. Work out the mean and the standard deviation for the wingspans of the giant ibises. Right, well, first of all, I better work out the mean of the coded data, I guess. So the mean of Z is going to be 104 divided by 20. So the mean of the coded data is 5.2. Okay, so now let me convert that to Y. So the mean of Y would be the mean of Z times 10 plus 5, which is going to be 5.2 times 10 plus 5. Looks like 57 to me. Okay, so that's the mean of the coded in red and the mean of the raw data of Y, of the actual data, in blue. Right, we've got to work out the standard deviation of the actual data, the standard deviation of Y. So let's work out the standard deviation of Z. So that's going to be, standard deviation of Z is going to be the square root of the summary statistic over n. Well, n is 20, isn't it? So the square root of 1.8 over 20 gives me a standard deviation of 0.3. So now in blue, what will the standard deviation of Y be? Well, Y has been made a factor of 10 times smaller by the coding. So the standard deviation of Y will be 10 times larger than the standard deviation of Z, giving me a standard deviation for Y of 3. And that is question 12 complete.